We have already discussed the propagation of light signal through the optical fiber using geometrical optics, that is, with the help of total internal reflection. Now, geometrical optics will be valid if the light wave is transverse electromagnetic in nature, right? Again, to propagate transverse electromagnetic wave or transverse electromagnetic light, the medium must have semi-infinite extension in the lateral direction. Okay, that means in the lateral direction it must have certain region where the wave will not be restricted. Unfortunately, inside the core of the fiber, where the core is of the order of few micrometer only, whereas the wavelength of the light is of the order of micrometer. Okay, under that condition, inside the optical fiber, transverse electromagnetic wave, particularly for small core uh, optical fibers, transverse electromagnetic wave doesn't exist. So obviously geometrical optics will not hold. Okay, so we cannot explain the propagation through the fiber using geometrical optics. So what is the other alternative? Other alternative is to solve the wave equation inside the optical fiber. Okay, so let us start with the Maxwell's four equations. The Faraday's equation, curl of E equal to minus del B del T. Ampere's law, curl of H equal to del D del T. Gauss's law, del dot D equal to 0 and del dot B equal to 0. Okay, so this electric field E, this is auxiliary magnetic field H, this is magnetic induction, this is displacement vector D, and there is a relationship D equal to epsilon into E and B equal to mu into H. H is the auxiliary magnetic field, mu is the permeability, epsilon is the permittivity of the medium. So using these four equations and combining these two, we can write the wave equation, that is del square E equal to mu epsilon del 2 E del T square, and for magnetic field we have del square H equal to mu epsilon into del 2 H del T square. Now mu epsilon can be written as 1 by Vp square, where Vp is the velocity. Okay, now instead of writing this vector equation, let us convert it into equivalent scalar form. Okay, see, for this equation we have three components, for this equation we have three more components, right? And we have to solve all the three components if we want to get the total solution. So instead of doing so, first just consider the equivalent scalar form. Okay, so it is del square psi equal to 1 by Vp square del 2 psi del T square. Okay, and Vp is equal to, we have just said that it is phase velocity 1 by mu epsilon whole to the power half, that is mu r epsilon r into mu 0 into epsilon 0 whole to the power half. Mu r is the relative permeability, epsilon r is the relative permittivity, mu 0 and epsilon 0, these are the permeability and permittivity of the free space, right? Now in cylindrical coordinate system, we can write the expression for this Laplacian operator in this way, that del square psi equal to del 2 psi del r square plus 1 by r del psi del r plus 1 by r square del 2 psi del phi square plus del 2 psi del z square. This is in the cylindrical coordinate system. Why we are using cylindrical coordinate system? Because the fiber itself is cylindrical in shape. So it will be easier for us to solve this wave equation in cylindrical system. So this is a standard equation and there is a standard solution. So psi equal to psi 0 e to the power j omega t minus k dot r, where k is the wave number 2 pi by lambda. Okay. So basically this is the basic solution. We can extend this idea to electric field and magnetic field, right? But that particular process of solution of electromagnetic wave is very rigorous, right? So instead of going through the mathematical jugglery, we will basically try to confine our discussion in the uh, argument level. Okay, so we are not going to discuss all those mathematics in this class. Here we have the propagation coefficient n1k cos theta, where theta is this angle. Okay, this is the light wave and this is the angle, and this is the x component, this is the z component, n1k into sine theta. Okay, so wave vector is n1 into k here, right here. So this is x direction, this is the z direction. Now the wave, if we consider a particular wave that will produce an angle of theta inside the fiber, this angle theta. Okay, and all these rays are reflected in this way. So one portion of the ray will be reflected in this wall and other portion of the ray will be incident on this wall, and actually it is a conical shape, right? It will produce a conical shape. It will be reflected throughout the cylindrical surface, right? And then they will meet at this particular point, and then again they will go to the other side, right? So in this way you can see sometimes the wave will be confined within the axis, near the axis, and sometimes the wave will be distributed over the cross section of the fiber. Okay, so electric field will be like this. Sometimes it will be higher, sometimes it will be lower, and in this way the electric field will propagate. But if we consider the distribution of the electric field, hmm, you will see that at the midpoint or on the axis the electric field strength will be highest. Okay, and as you go uh, towards the end of the core, the amount of electric field will be lower and lower. Okay, but for if we consider the proper um, uh, calculation, hmm, you will see that small amount of power will also present inside the cladding region. That means for geometrical optics, whatever we said that no power will go to the cladding, whenever we will go for the analysis of electromagnetic wave using Maxwell's equation or wave equation, you will see some power will be there in the cladding region. So effectively, uh, the area of the core will be slightly increased. Okay, so you must remember this idea. That means all the power is not confined within the core. A small amount of power will be available in the cladding region also. Okay, and it is coming because of the this power is coming because of the analysis we have performed in the using the Maxwell's wave equation. In geometrical optics, there should not be any power in the cladding region. Okay. Now we have already seen that in our previous slide, we have seen that most of the power, maximum amount of the power, will be confined on the axis, and as you go on, go towards the cladding region, the power will be reduced, right? But depending on the incident angle, right? Depending on incident angle, that is the tilting of this ray. Depending on this tilting of this ray, we can have two portion, rather it is a ring kind of shape, where you will get the maximum electric field. Okay, so here we have maximum, if you consider it is a cross section of the fiber. So here we have the maximum electric field, and here we have a maximum electric field. So that means the electric field will be maximum over a ring, right? Now if we change the direction of the incident ray, then it may happen that here we have one maxima, here we have another maxima, and here we have another maxima. If we change the tilting angle again, you will see we have number of maxima, like here we have one maxima, here one, here one, here one. So that means whatever we are observing, that depending on the incident angle of the ray, the electric field will have different distribution. Sometimes it will be maximum at the center, sometimes the maximum will occur in the ring, sometimes we have number of rings, concentric rings, right? Such distribution of electric field is referred to as the mode. Okay, so the picture is showing the transverse electric field patterns. So these are the different modes. For m equal to 1, modes are identified in with the number, that m equal to 1, like m equal to 2, m equal to 3. So more the mode number, higher will be the incident angle, and number of maxima will be higher. Okay, so it is clear, it is evident that inside the optical fiber, different distribution of electric field is possible, right? And that distribution is basically dependent on the incident angle. Okay, so these are called the modes.